We could make this out of a piece of superconductor, because I just told you I can pass a current without dissipation to a superconductor. Unfortunately, what happens when we do that is eventually the superconductor stops becoming a superconductor because the very thing that was pinning the magnetic field and the flux lines here causing this to levitate, my sneaky trick, those vortices start to move and that causes dissipation and then the thing heats. And suddenly, instead of passing current through something that's a reasonable conductor like copper, we're trying to pass a lot of current through something that's a really bad conductor, and we probably melt our magnet. So you can commercially get superconducting magnets up to around 20 Tesla. The Highfield lab in Tallahassee, which is our sister lab, we're all funded through the National Science Foundation as a user facility. There they have a 45 Tesla magnet, which is a superconducting outer magnet. And then to solve the problem of the superconductor not being a superconducting high field, they put a resistive magnet inside, but they have to pump thousands of gallons of water a minute through this coil of copper to keep it cold and stop it from melting. So the limit there of having a magnetic field we call DC field that you can switch on and leave on for hours at a time is not just how much current you can pass, but how much cooling power you've got. And the world record there is about 45 Tesla. To put that into context, grab one of these super strong, these super strong magnets here that will probably stick through my hand if they're, yeah. So they're pretty strong. That's far enough apart that it's not hurting me. If I get them too close, I won't get them apart again. The field at the surface of these is probably getting on for 1 Tesla. That's a super strong neodymium iron-boron magnet. Your fridge magnet is a small fraction of a Tesla. The Earth's magnetic field is a few millitesla, I think. It's tiny, but a huge volume. Okay, so we can get to about 45 Tesla just by being able to keep our conventional conductor cold enough by pumping huge amounts of water through this. This facility uses something like 10% of the power demands of the city of Tallahassee, where it is when it's up and running. What we do here in Los Alamos is we're the pulse field facility. So we get away from this heating problem by turning our magnets on for a very short period of time. So I take my coil of wire and first of all I get it cold. That does 2 things. That first of all puts me further from the melting point. It also makes my conductor a better conductor, because as I said, one of the definitions of a conductor is it gets better as it gets colder. It also makes the materials that's holding the coil together a little bit stronger. And then I basically pulse a very large current through this, and that generates a magnetic field for a short period of time. So let me grab my 65 Tesla magnet from outside. So
hold it up so we can see it.
Stand on the chair. It's about.
I'm kidding.
It's it's too heavy. The conductor in this these are the leads. These are the terminals. To power this magnet, we use a capacitor bank about the size of the bar here. The reason we do that is we want a very high current for a very short period of time, and the capacitor bank basically acts like a reservoir, and then we open the sluice gates to the dam and boom, the current will flow very quickly. We can't get that much current even out of our substation, just out of the wall in a controlled way. So the conductor inside this comes across and down, and you can see the bore of the magnet, as I said, is about the size of my pinky finger. It's got multiple layers, and then wrapped around the outside we've got some of the world's strongest material. This has different bands of steels and Xylon and organic fibers, Kevlar, things like that, carbon fiber that actually hold this together. So this is now what limits how we make magnetic fields, is not the fact that it's going to heat if we make our pulse short enough, it's how this magnet actually holds itself together. So again, we're going back to our Lorentz force thing. The electrons, as they go around in a circle, experience a force, but the electrons in the magnetic field are also experiencing a force, and so the conductor is. And so the magnet in the magnetic field wants to do this and do this. And so we're basically limited by the strength of the materials. So this will generate 65 Tesla. We do this routinely. It takes us about 40 minutes to cool it back down to liquid nitrogen temperature. We pulse it. The rise time of the pulse is about 10 milliseconds. The total duration is about 100 milliseconds. We take all our data and our measurement in that time. And then we wait for, I'm going to close the door because I'm getting a draft. And then we wait for about half an hour for the magnet to cool down again, and then we can repeat the measurement over and over. The sample, the materials we're interested in, are typically smaller than you can see with the naked eye. They've maybe got 4 or 5 wires on them, maybe they're in a magnetometry coil, maybe they're stuck to a fiber optic so we can measure their optical properties or the length change. They're inside a cryostat. That's basically a fancy thermos flask. So this is in liquid nitrogen. We might then have a vacuum space, then liquid helium, then another vacuum space, maybe the isotope of liquid helium-3 will get us down to about half a degree above absolute zero. And in that way, the magnetic field can be the dominant energy scale in the problem. Because although it takes about 1.5 megajoules of energy to power this, that magnetic field strength is still rather weedy compared to temperature. Meaning, for an electron, typically 1 Tesla is about 1 Kelvin. So room temperature is 300 Kelvin. If you wanted the magnetic field strength to be dominant at room temperature, you'd need a 300 Tesla magnet. A magnet that goes to 100 Tesla is basically this inside another magnet, inside another magnet. It's like Russian dolls up to about this size. Now the reason for that is basically you're distributing these huge forces and these loads that the magnet wants to rip itself apart. But as you do this, you get into this sort of runaway solution. I put my reinforcing material, and then the next coil around the outside is even bigger, so then I need even more energy to power, more power, importantly, how much energy per unit time you can get in the magnet, and it gets bigger, and it gets bigger, and it gets bigger. Luckily here in Los Alamos we have this great motor generator system, so the capacitor bank to drive this is a 4 megajoule bank. We typically pull off about 1.5 megajoules to power this magnet. To power the magnet, by the time it gets this big, we're talking about 200 megajoules. A capacitor bank that size is the size of the particle, or more. We actually do this with rotational energy. We have a motor generator. This thing's about 50 tons of rotating mass. We spin it up from our substation. We disconnect it. It's idling as a rotational source of energy. And then we basically connect it through some very fancy power supply rectifiers that create the waveform we want, and that energizes our big magnet system.
But when you're dealing with, say, 100 Tesla, you're getting stresses getting up close to 1 million PSI, right? So how do you deal with that?
Careful. So we try. So basically, we're distributing it over many layers. So in that magnet, the inner part of the magnet is actually very similar to this. It's wound, and it's driven by a capacitor bank to be a rather short pulse magnet, going up and back in about 10 milliseconds. The outer magnet becomes slower, and then we have steel reinforcing. We have some of the world's strongest steel. The pressure, the force per unit area of those coils on those reinforcing shells is about 30 times the pressure at the bottom of the Marianas Trench. So when James Cameron was incredibly brave a couple of years ago and sat in his little submarine and was the 2nd or 3rd person in history to go to the deepest ocean on Earth at, 30-something thousand feet, he's 10 kilometers down, we're dealing with pressures that are 30 times that. And that's basically approaching the yield strength of all known materials. And so every time we pulse the magnet, we're basically running up to the plastic deformation limit of everything. The conductor, the reinforcing material, the dielectric material. So if you, actually I can pass this around and you guys can see. You've all played with copper wiring in your home. Copper's a really soft, malleable metal. You'll see this thing's way more like a steel spring. This is mainly copper, but we have various alloys of copper. This is probably what we call Glidcop, which is copper with alumina powder in it, sapphire, aluminum oxide. And that basically, a bit like putting gravel in your cement to make concrete, makes it a tougher material, means that it's harder to have dislocations and bend it. There are other other things you can do, a bit like putting rebar in there to make it stronger, copper niobium, copper silver. There are other alloys that basically you're trading off the conductivity, how fast it heats,